Hi, my name is Hari,
And my name is Tony.
and this is our project on training a recurrent neural network guided car to navigate through hallways. Although self-driving tech has come a long way, there is still room for improvement. Tesla, with their autopilot, have been the most sophisticated self-driving system on the market, but it's far from being autonomous. This picture on the bottom left is from the Society of Automotive Engineers, and Tesla's technology would be categorized as level 3, meaning that they can detect collisions and adjust driving speed, but still need user input to drive safely, as we will see in the next slide.
Someday, yeah. Eventually.
Oh my god, có thằng taxi quanh nóc đường.
Holy sh! Holy They should have seen that.
Did you video it?
Yeah, but I don't think it was gonna turn, huh?
Did you save it? Save it.
Well, it didn't look like it was turning.
No, it's not.
Hey, it's Scott Kubo. So I've never driven this road before, and it was definitely a close call with autopilot, but fortunately I took over just in time. You can see at the end I clicked on the screen to save the dashcam footage so we can take a look at that later. Now this was with autopilot version 10 2019.32.12.1, and you can see pretty clearly that lane converges into that concrete barrier, but when we zoom in we can see that autopilot is displaying a continuous lane that seems to keep going straight.
So the topic of ethics is also ambiguous. Recently, Tesla unveiled a summon feature where users can hail their car from a parking lot, and one of these cars, while being driven autonomously, rolled through a stop sign, and the cop did not know whether to give the ticket to the driver or not because he technically wasn't controlling the car at the time. So to explore and mitigate these problems, we plan to have stop sign recognition as well. And lastly, substantially less work has been done with smaller vehicles like those that can be used for rescue missions or where there's a clear objective. This can be useful for, say, an earthquake rescue robot.
So, our plan was to create training data using camera video, a LiDAR sensor, and data about the car's movement, such as which way the wheels are facing and how much power is going to the motor. We would then drive it through the school's hallways, trying to stay away from the walls. Our plan from there was to format and feed the data through a long short-term memory recurrent neural net, and then have the neural net drive the car. On the slide is an output from the LiDAR sensor made by putting 3 containers together.
Firstly, a brief overview of what the terms LSTM and RNN mean. A recurrent neural network, or RNN, uses previous output states in the current input when computing the current output state in order to better generalize patterns in data. Driving, for example, lends itself well to time series data. A long short-term memory cell, or LSTMs, are a type of neural net cell that is designed to be used in RNNs. They have logic gates within them that determine which information from the previous output to consider when computing a novel output. They have the ability to become perceptive to long-term patterns that occur over time. We hope that by formatting our data in time series and feeding it to the network, it will learn to generalize patterns of human-like driving.
To get training data, we wired up a controller using an Arduino instead of using the controller that went with the car. You can see our early version of the controller with 3 steering settings, left, right, and center, and a potentiometer controlling the motor on the slide. We eventually swapped the 2 buttons for another potentiometer to get more steering range. The LiDAR sensor we use to remotely sense the car's surroundings works similar to radar, but instead of radio waves, LiDAR uses light waves and finds distance by measuring the time it takes for a light wave to bounce back to the sensor. We use the LiDAR sensor to create a mapping of theta distance pairs around the car. Ultimately, we ended up not using the camera because we spent a lot of time setting up the LiDAR sensor in car control and did not have much time left to work on the camera. We also briefly tried making a website to control the car, but dropped it in favor of a physical controller. To format the data into matrices, we pulled data from the 2 text files, one with the LiDAR data and another with the car data. On the left, we can see part of a LiDAR text file with theta and distance pairs. On the bottom right is part of a car data file with a timestamp followed by motoring and steering values. We created mappings by finding the closest times between the timestamps in the two text files and mapped lists of theta distance pairs from the lidar text file to steering and motor values from the car data text file. One thing we had to consider, since we used timestamps from both the Raspberry Pi and a laptop we used to get car data, was the small difference in time. Before we start each training session, we tried finding this difference by getting the time on both devices at the same time and factoring the distance when linking the two sets of data together. On the top right is part of a process matrix created from the training data, where we tried normalizing the data, which Harry will talk more in depth about.
So we essentially took the theta distance pairs, and in order to satisfy the shape of the LSTM cell, we essentially listed them in the order they appeared, letting the order of the data serve as the information for the theta value. And we normalized the distances so that the neural network will have an easier time training. The two larger values at the end correspond to the throttle and steering values, respectively. So we broke up our one long time series data series into smaller chunks that the neural network could train on. We wanted to pick windows of time that were large enough to contain patterns, but small enough to be evaluated fast enough in real time. We used a list comprehension in Python to break up the data, where the variable time step is the size of the individual windows of time, and the variable div controls the lack of overlap between the different windows. In our training, we used a timestamp of 30 and a div of 1, meaning that we had a large overlap in our different windows. The picture on the bottom right describes the structure of our recurrent neural net. Although we could not gauge our performance, it is clear to us that we would definitely need more training data in order to create an accurate model. Given more time, we would run the model live using the car and monitor its responses. For example, if it were prematurely turning into walls, we would purposely crash it in a similar manner a few times and recover the car manually to teach the network to do the same. A large piece of advice to those attempting similar research is to perhaps use a non-proprietary method of control. We ended up working with the Traxxas RC car, but its controls were not meant to be modified by a microcontroller. If we had used a platform such as a donkey car, we would have plug-and-play functionality, saving us more time, allowing us to incorporate more features like stop sign recognition and allow us to focus on optimizing the network.
We'd like to thank several people for supporting us. Our project would not have been possible without their help. So first, we'd like to thank Dr. White and Dr. Zacharias, our computer systems lab directors, for mentoring us, Mr. Bell for helping us with the controller, Mr. Sila for giving us advice with the XBs, Mr. Kosek for his help with our website, John Butner for setting up our project to work with TJ servers, and finally, the TJ Partnership Fund for providing us with the materials for our project.